My name is Aditya Natu and I'll talk on electrokinetics of polymeric fluids in narrow rectangular confinements. It's a research paper authored by me and Professor Aditya Ghosh and I will be presenting it. Here is the problem statement. We have a long rectangular channel in which a fluid is flowing. The fluid has an electrolyte dissolved in it which dissociates into positive and negative charges. Now, the positive charges are adsorbed on the walls, leaving the bulk of the fluid negatively charged. The negative charges are concentrated near the walls since they are attracted to those positive charges, and we get an electrical double layer. The layer closest to the wall is called the Stern layer, and we assume that it has a known electrostatic potential zeta star. Now remember that all quantities with a star are dimensional quantities, while those without a star are non-dimensional. We may or may not apply a pressure gradient. We have chosen characteristic scales as shown on the slide. Some dimensionless quantities emerge when we non-dimensionalize the governing equations. The Deborah number tells us how large is the relaxation time of the polymer as compared to the time scale of the flow. We then have the aspect ratio R. Kappa tells us how large is the channel height compared to the Debye length. The Debye length is the length across which the effect of the charged walls reduces significantly. The ionic Peclet number tells us how prominent the advection of charges is over their diffusion. The Dawkins number tells us how conductive is the Stern layer in comparison to the bulk of the fluid. Similar to the pressure-driven velocity scale, we also have an electrokinetic velocity scale and alpha is their ratio. Now here are the governing equations. The continuity equation is essentially the mass conservation equation. The Poisson-Boltzmann equation tells us how the electrostatic potential is distributed. Next are the x, y, and z momentum equations. Now, two types of electric currents flow in the liquid. First is the streaming current. When charges flow along with the fluid, it amounts to an electric current called the streaming current. Now, if an electric field is present across the channel, it leads to conduction. If no electric field is present, the total current should be zero, right? So when a charged liquid is flowing and thus causing a streaming current, while no external electric field is present, a potential gradient is automatically developed across it, which sends a conduction current in the direction opposite to the streaming current. This potential gradient is called the streaming potential. Our fluid is non-Newtonian, so we use two models to describe its behavior: the simplified exponential Fan-Tanner model and the Gauss model. Now, here are some of our results. It's interesting to note that in the Gauss model, the flow in rectangular channels cannot be unidirectional. Along with the axial flow, we see circulation as shown in the streamlines. Another interesting result is this. We plot the average velocity against the aspect ratio. The dotted lines show the average velocity for flows in infinitely wide parallel plate channels, which we obtained from the existing research papers. As our aspect ratio increases, our average velocity approaches the value in infinitely wide channel flow. But as the Deborah number increases, the wide channel flow gets worse an approximation of the rectangular channel flow. This is one reason why analyzing a rectangular channel is important. Finally, here are some more graphs. We see how the gain of streaming potential increases with the shear thinning of the fluid. We vary epsilon, A, and the Deborah number. Epsilon is a non-dimensional parameter of the simplified exponential Fan-Tanner model, and A, known as the mobility factor, is a non-dimensional parameter in the Gauss model. We also vary kappa and thus go from thick to thin electrical double layers and plot the variation in streaming potential. This concludes the summary of the results. Thank you for watching.